Hey everyone, in this video we will discuss the free fall acceleration of a can dropped from rest from some initial height. Alright, so what we want to solve for in this problem is how much time does this can spend in the bottom half of its fall? Okay, so this video assumes that you have already spent time going through, familiarizing yourself, and studying the section on freefall acceleration and 1D kinematics. Okay, if you haven't, please go back and do that before watching this video. This should not be your first introduction to freefall. Okay, so now moving forward, assuming that you have done that, let's start the problem. So, as with any problem in physics, right, I want you to just make a sketch, make a drawing, a crude sketch. It doesn't have to be anything extravagant. This is my 40-meter ledge. So I'll say that's 40 meters, right? Height equals 40 meters. And this can, which I'll just denote as a dot, right, starts at the top of it, right? And so because we want to find the time in the bottom half, I'll go ahead and split this height into two. So we want to find what I'll say is T2, which makes the time in the top half T1, okay? So a couple key things about this is that it's released from rest, right? Released how, it doesn't matter, it's just released from rest. So that means that the initial speed, which we write as V naught, right, V sub 0, is equal to 0 meters per second, right? And by the way, that sub 0 is pronounced V naught, right? It's just what physicists use. It's kind of old and antiquated, but just roll with it. Okay? V naught. Because it starts from rest, that is 0. We don't know the final speed, okay? And no, the final speed is not 0 either, right? What we're only worried about is what happens just after it's released, right? And then it accelerates down, and then just before the micro iota of an instant, just before it strikes the ground, okay? So the final speed is not after it strikes, bounces, and comes to a rest, right? So it's not 0 and 0. It's the speed just before impact. That's the final speed. So V final, we don't know, okay? All right. So that height of 40 meters implicitly tells us that our 0 height is at the bottom, right? Which also implicitly tells us the positive direction. The y direction is going up, right? From 0 up to 40, right? So the equations in table 2.1, right, the basic kinematic equations that you will use for one-dimensional constant acceleration problems, those were written only in terms of x. I will tell you right now that you can input y in place of x, right? The same equations hold. And because this is not an x dimensional problem, I'll be using y because that makes the most sense, right? It's a vertical problem. All right, so about this, can we find straight away the time in this bottom half? Well, when this is released, it's going to accelerate down. It's going to be moving at some speed right here at 20 meters, and it's going to end up at some faster speed. In order to find and calculate the time here, we need to know both of those speeds. But we don't know either of them. So we cannot straight away solve for T2. We have to piecemeal this, okay? And I suggest trying to find the time for the entire fall. Okay, what's the time for the entire fall? Well, let's see, what equation can we use? We can use a couple. Let's see, one of them is this one. V naught y of t plus 1/2 g, or sorry, let me write it like this. Okay, now take a look at this equation right here. Okay, it's in terms of y, not x, and each of these terms is in terms of y. And that's important. We have to specify this is the initial speed in the y direction. It's not simply v naught t, right? It's not v naught t. It's v naught y and t. Just like over here, it's 1/2 a in the y direction times t squared, right? It's the acceleration in the y direction times t squared. You don't have acceleration in the x direction for free fall because there is no acceleration horizontally, right? There's only acceleration down. So over here on our sketch, acceleration in the y direction is simply what we call little g, the local acceleration due to gravity, which is equal to 9.81 meters per second squared. Okay. So if this was an x equation, that term wouldn't be there, right? But it's a y equation, thank goodness, and that's what we'll use. All right, so we need to rearrange this or put it in slightly different terms. We want to solve for the time at the very bottom, right? So we have time there. Let's see, y naught plus v naught y, that turns into v naught times sine theta times t plus 1/2 g t squared, right? Does anything cancel out here? Right? I put this in more specific terms, which is handy for later problems, but it turns out that this middle equation, or this middle term, goes away, right? The initial speed, v naught, is 0. So that term entirely is 0 and goes away. So we're simply left with these now. 1/2 g t squared. Okay? And by the way, we have to change this as well. This acceleration that I've inputted here as g, right? This acceleration is going down, right? G is going down. So you can put it right there if you want to. Gravity always points down. That's in the opposite direction as our positive direction, right? So that means that this sign right there, well, that's a big eraser, right there and there, has to be a negative. Okay? What we basically wrote was this, right? So that sign of that last term is negative. And now we can solve for t for the entire fall, right? Let's see, take that over to the other side. We have y naught minus y times 2 over g, and then square root of all that. Okay, so let's plug in some numbers here. We have 2. Y naught is the initial height. That's 40 minus the final height, that's 0, the ground, divided by, that should be a g, sorry, divided by 9.81, and square root of all that, right? If we do that, that should be 2.86 seconds, okay? So that's That's the total time. I don't know if you want to capitalize this t or not, but that's the total time. Okay. What other time can we find? Okay. What other time can we find? We can find t1. We know the initial position. We know the final position, 20 meters, right? And we know the initial speed, right? So if we can get the total time of flight, right, or total time in the air, and if we can get this first half time, we can subtract the two to get the time in the second half. So let's do that. So, well, can we use the same equation? Yeah. Let's do it. Let's do it. So y equals y naught plus v naught y of t. I'm going to go ahead and input the negative g, right? And again, v naught is 0, starts from rest. So it's pretty similar to what we just did, right? Except this time is actually time 1. So we can solve for time 1. In this case, there we go. In this case, the initial height is 40 and the final height is 20, right? For this middle time, or this time here, the final position is 20 meters. And g is a constant 9.81, right? In this case, it should be a value of 2.02 seconds. And now we can just subtract 2.02 from 2.86. And T2 should be the difference of 0.84? If I do my math all right? Seconds. Right? And that's our answer. All right, well, thanks for watching.